All right, in this section, I want to show you how to compute partial derivatives of functions of two variables. We'll also see how you can do it for functions of 3 or 4 or 5 variables, as many as you want. So rather than start with definitions and the formal things, I wanted to just start with an example because once you see how to do it, it's really not too bad. So once we've seen the example, then we'll come back and learn what's really going on behind the scenes. So here's the idea. You can take a partial derivative with respect to either variable that you want. In this case, either x or y. I'm going to take the partial derivative with respect to x. First, we'll talk about notation in a minute, but we usually write that f sub x. And all you do is you imagine the y's as just being constants. So this is a constant, and this is a constant. It's like it was a 2 or a 5. And you just take the derivatives of the stuff involving x's. So here for f partial x, I get a 3x squared plus a 2x constant comes along, so y cubed, and then 0, because the derivative of this with respect to x is 0. For f partial y, I get the derivative of this, and now I'm holding the x's constant, so the derivative of this is 0. This is a constant, so I get a 3. Usually I write the x's first, so I get a 3x squared y squared, and then I get a minus 4y. So these are the partial derivatives, partial derivatives of f with respect to x and y. And now if you want, you can actually plug in specific points, and so we're going to talk about that. What's the actual meaning? So just notice that f partial x evaluated at 1, 1. You get out of 5, f partial y evaluated at 1, 1, you get out a negative 1. And so you can plug points into these and you get out numbers. And so our goal in a little bit is to learn the significance of those numbers. What do they actually mean? All right, so now that we've seen how to do it, we want to ask ourselves what's really going on. And I want to give you the formal definition, and you'll sort of see how we're holding one variable constant. So here's the definition. The partial derivative of our function f with respect to x. Now I'm going to define it at a specific point. So at the point AB, we're going to write this like this. This is defined as, here we go, f partial x at the point AB. It's the limit as h goes to 0 of f of a plus h comma b minus f of AB all over h. And I would love for you to take a moment and pause the video and either look back in your Calc 1 notes or look in your book or look online or do something. Look up the formula for the derivative of a function of one variable. And you'll see that this is almost identical. We're just letting that y component just stay constant. So here we're holding y constant. Y is just b. And we're letting the x component vary. So we're studying the limit just in the x component. And so that's exactly what's happening when you compute f partial x. You're holding the y constant. And so maybe we can write that down. We can say y constant here. And then a similar definition for the partial derivative of f with respect to y. We denote that f sub y. We're going to define it at a point. And it's f sub y of a. AB is the limit as h goes to 0. Now we're going to hold the x constant, so a comma b plus h minus f of a comma b all over h. And here we're holding the x constant. Of course, either one of these limits, this one or this one, might fail to exist. That's always possible when you're talking about limits. So the big question is, are the partial derivatives defined? So on and so forth. So what I want to do next is switch to the Mathematica screen and try to show you visually what's happening. So let me tell you while we're here, these derivatives that we're writing down, these are just Calc 1 derivatives. It turns out that we're taking a surface, let's say that our surface is like this, we're slicing it a certain way, and then we're getting a two-dimensional curve. And so you're going to see that these numbers are just slopes of tangent lines to two-dimensional curves, just like we saw in Calculus 1. So to see that, let's switch the screen to Mathematica. All right, so I want to visualize what partial derivatives are all about. And if you can get the picture in your mind and understand, it really helps make sense of things. So I've given us a graph. This is z equals some function of x and y. In this picture, I fixed an x value. When you fix x, you're talking about partial y. So I'm fixing x, I'm holding x constant, and now I can see that when I do that, just like we did traces before back in 10.6, fixing x results in an intersection curve of your surface and the plane associated to your x value. And this curve lives in the y and a mirror image of the yz plane. It's not x equals 0, but it's in a similar yz plane with x equals whatever x is. And please realize this, because z is a function of x and y, this curve will be a function of y. This is always going to be a function. The curve that you get is a function. And so all of a sudden, this curve floating here in a copy of 2 space, you can talk about the tangent line to the curve at any point, just like we did in Calc 1. And so let's scroll down. I picked a different situation, a different curve here, different surface, I'm sorry. And so I want to, again, fix x. When I do that, I get an intersection curve. And all we're doing when we're computing partial derivatives is we're computing the slope of the tangent line to that curve. So this is an f partial y, and I can slide my x around. The top control, let me move it to the side where you can see here. The top control, yeah, there we go. Top control is changing my x values. When I change x, I get a different intersection curve. Do you see how that curve is changing? Okay, the bottom control changes y. And let me zoom it around here where you can see. It's a little hard to navigate without my regular mouse, but we'll make it. So as I change y, I'm changing which point I'm looking at on that curve, and you can see the slope of that tangent line. That I've actually got the full tangent line on there changing as you go up and down around the curve. So that's what partial derivatives are. They're actually just derivatives from Calc 1. So this was all fixing x, taking a derivative with respect to y. Of course, you get almost the same picture if you go the other way. Here in this picture, let me scroll up here and try to navigate this. Here I am fixing a y now, right? Let me scroll down where you can see the axis. Yeah, there we go. You can see that I've fixed a y. When I do that, I get an intersection curve. I'm so sorry. I can't control this very well. When I fix y, I get an intersection curve, and you can see that in black. And then as you let x vary, right, you're just sliding up and down that curve. So the bottom is controlling my x value, and that just drags that tangent line up and down and around the curve. Whoops, no, I'm sorry. The bottom is still y. So the bottom is telling me what y value to pick. Let me scroll around where we can see it. Here we go. Yeah, so the bottom is my y. I fixed y now, and now I'm going to let the x value slide up and down and around, and you can watch that tangent line adjust as we fix x. So same kind of picture, just depending on which variable you're holding constant. All right, so how do you visualize all this? In your mind, I just need you to realize when you take a partial derivative with respect to x or y, whichever the other variable is, you're holding that variable constant. That gives you an intersection curve, a two-dimensional curve, and the partial derivative you're computing when you plug in a point is actually telling you the slope of a tangent line to that curve. We rarely will need to actually see that, but it's really helpful if you know in the back of your mind that's what's going on. All right, so we'll end this video here, and we'll keep going in the next one.